So this lecture is called Gaming, Game Playing, and it goes into the theory of artificial intelligence as it's applied towards game. There's an entire chapter in your book on this concept. And this concept is actually on your midterm exam in terms of two of the questions, or one of the questions actually, which has a game with some boxes where you move pegs between one and the other, or something similar to that, I believe. And that gives you the opportunity to kind of see how you develop a solution for a game. So I'm going to talk about is gaming theory, the concept of generating solutions for games. I talked a little bit about it actually in the last lecture when I talked about dice and craps and card games. And applying it towards Bayes networks, you can actually sort of figure out a solution using a networking with a probability and a statistical analysis kind of problem-solving approach. Games are done a little bit differently. They're more about eliminating paths and getting to the goal, and goal-focused. So the idea of the game is you want to win. So you can generate and test. That's what the slide's basically going to start out with. Search can be viewed as a generate and test procedure. So we figure out, if we do this, this, and this, are we going to win? So you can generate a process, you test it out. Oh, yeah, we won. And it's a learning kind of system sometimes because you have to figure out, well, what moves? So there's people who are really good at this mentally, and they play chess and checkers and tic-tac-toe, and they instantly win. In fact, everybody in here has probably played tic-tac-toe enough to know how to win. Yeah, so you've won the game. But an artificial intelligence program would take a harder game and make a solution out of it. So that's really what we're talking about, what I'm talking about for this lecture. Testing for the complete path is performed after various different amounts of works are done by the generator. So then after we figure out the likely solution, then we test out a series of likely solutions in terms of the problem-solving approach. So at one extreme, the generator generates a complete path which is evaluated, and that hopefully turns out to be the correct path. At another extreme, each move is tested by the evaluator, and it's proposed by the generator to know that, is this a good move, is this a bad move? So one of the questions of the midterm is dealing with this lecture, which is why I've chosen to go over this lecture, although it's not on the final. It is on your midterm, which is your final, yada yada. But long story short, you have to map out all of the different possibilities of moving A and B together so that A gets on this side of the field and B gets on this side of the board, and you're going square by square, or you're going jump by jump, and you're following the rules to generate a series of different combinations that it's going to work. So you have a problem-solving approach. So improving the problem-solving approach, you can do all sorts of search bases and search solutions. And the actual question on the midterm is actually giving you the opportunity to create a search tree as the solution. I start out and I give you a couple and I give you a point system that goes along with it for winning. So there is a way of determining who's going to win depending upon what moves are made and in what order. So two options are available to improve the search-based approach: improve the generator, obviously, or improve the tester. So the generator only generates good moves or paths. So we can have a generator that just generates everything. What we have to now put some logic on, well, what's good, what's going to bring us to our goal, and then also what's useless, what should we not do. And it's kind of like the effect of, let's say, for example, a tic-tac-toe game. You can make a tic-tac-toe game run a long time by filling in all of them until, oops, we got it. You can have some moves that don't make any sense, or you can have multiple options that you can play. That's not really an optimal solution. If you had one way of doing it, then you would be goal searching, and you would be looking and generating solutions that are going to lead you to the ultimate win as quickly as possible, the fewest number of moves as possible. Also improving the tester, so the good moves are recognized early and they're explored first, so that the tester isn't doing things they don't need to do, irrelevant moves. That was just kind of interesting. Have you ever seen, like some of those, I don't know, they're like TV demonstrations of people playing chess, and one guy comes in and with one move wins the game. So that's a better tester because he's not going to make all those other moves you don't need. In fact, if you've ever watched professional chess players, it happens quickly because there's only a couple of different combinations and they're not done yet. Like they get to a certain point where it's inevitable that this person's going to win, and then both people actually see it ahead of time, so okay, you won. And he's like, wait a minute, I got 20 moves left I haven't done yet. That's a good tester. And a good generator gives you a mapping so that you only make the right moves in the right order, and you don't do moves that don't make any sense for the win. So using a generate and test approach can be used to solve the identification problems of small search spaces. The problem you have in the midterm is an extremely small search space. You have like 5 or 6 blocks, and you have a A peg and a B peg, and you try to move them in opposite directions. You only have like 4 or 5 blocks to move them in, or spaces or squares. You don't have that much, so the search space doesn't necessarily need to be big. So you want an optimal identification system to identify the moves. Can be thought of as being a depth-first search path as well, with backtracking allowed. Meaning, and hopefully at the end of this course, you hopefully know the differences between backtracking and forward tracking. If not, go ahead and read that stuff, because you're going to need it for you'll need it for a partial bit of a question on the final, actually. Can also be used as an expert system for identifying chemical compounds and things, which is kind of interesting. If we can take take a paint as an example and separate it out into its different components, and then we can figure out how the color was derived or how the chemical itself was composed. So we also have some dangers. So we can consider a safe cracker, trying to use a generator to test a test generator essentially, to generate a test to crack a safe with a 3-number combination. Well, that's pretty bad. The approach is not going to open up the safe in enough time before the cops get there. In fact, it'll probably be 2 or 3 days later. The guy will still be sitting there trying to crack this safe. Not such a good thing, because there are 100 to the third possible combinations. Safe cracker's going to take a week to go through that. So they got to use a different technique. You can't use this, exhaustive kind of approach. So at 3 attempts a minute, it would take about 16 weeks, 24 hours a day, 7 days a week to work through the combination of a systematic manner, which makes it impossible, which is kind of interesting, because sometimes that's how they design the combinations on locks and safes, because it's not feasibly possible for you to randomly generate or go through each one of the possible combinations. You might be able to figure it out, which is different than passwords, actually. If you go back to the concept here, if you're doing this manually, it's going to take this long. Well, what does it really matter if a computer program's doing it with a password generator and it takes them 5 days to go through it? Not a problem, or 16 weeks for that matter. The idea is you can crack it, which is different in the scenario, because it's not like in a secured area where there's going to be police showing up. They're not going to know you're sitting there for 16 weeks trying to crack a password, which makes crackword passwords kind of a feasible solution to use this brute force kind of exhaust all different combinations, because eventually you're going to find one. So what people have done in the past then is they said, well, make the password 7 characters long and put special characters in there. So it makes it reasonably hard. And then track the number of failed attempts, which is an easy thing right there. So in a software program, you can say, well, if the user logged in 3 times and it failed, lock it out, because we think we have a password generator who's going to go and kind of do that. So it makes the weak password kind of concept a little bit stronger by putting in more logic. So generator properties include complete or non-redundant and informed properties, characteristics that describe different generators. A complete one is capable of producing all possible solutions. A non-redundant one, you don't propose the same solution twice. Well, it means you have to keep track of the solutions you tried, which is kind of interesting. Or the informed one, where you make use of constraints to limit solutions being proposed, and you only try things that are feasible, which is how people do the passwords, actually. First thing they do is, well, okay, what's the dog's name? What's the cat's name? What's the person's name? And then obviously you have the 1, 2, 3, 4, 5s, 6, 7, 8, 9, 10, all the combinations of numbers people would think of. But birth dates actually are important. And believe it or not, like years are important, like fall 2013, or, certain passwords, spring 1995, it was a good year, so that's your password. Now I used to use my telephone extension. So I'm still using a telephone extension that I had to memorize from like one of my first or second jobs. It's like about 9 characters long, or nine digits long. It's a good password because it makes sense to me, and I had to memorize it. I know it, but who else is gonna? It means nothing. It was a randomly generated 9-number sequence that was my telephone extension, and I'm not gonna tell it what it is because it's my password practically for everything. But you never figure it out. It makes no logical sense. It's not my dog's name. I don't even have a dog. It's not. It has nothing to do with any piece of relevant information. So dealing with adversaries. Games have fascinating computer sciences because they run into a couple of different scenarios. You're either playing against the computer, or you're playing with a computer, or you have two people playing against each other via a computer, and you have somebody monitoring or somebody mediating in between. So we have Babbage, and this is kind of the historical kind of thing of games. He was the one that actually designed a tic-tac-toe machine. We have playing chess, analytical engines that play chess for us. Actually, there's a lot of them out there still. Shannon and Turing, well, they designed chess game algorithms in Turing, from the Turing machine, or Turing test, I should say. Samuels built the first significant game-playing system for checkers, actually. So people around computer science like to play games. In fact, a lot of computer science like video games, and that's actually kind of interesting. In fact, you can get books on most of the fantasy games, out there. How to win this one, how to win that one, and well, I was going to say Nintendo, but we've grown past Nintendo. I guess it's Xbox now or something. PlayStation games. They're fascinating because they're challenging, but they do take a skill, and it's because the player or the tester has generated significant analysis, hopefully, in terms of how to play the game. So the more you play, the better you get at it just naturally. So why games attract interesting computer scientists? Well, they seem to be a good domain for work, for machine intelligence, and were thought to provide a source of good structured tasks. So in which, success and failure is easily measured. We know that the program or the algorithm works when we win the game. So it doesn't require much knowledge either. This is later found to be untrue. The more knowledge in terms of tree structures or in terms of theory actually helps the game player. So chess. The average branching factor for each position is 35. Each player makes 50 moves in an average game, and the complete game has 35 to the 100 potential positions to consider. That's a lot, actually, which makes chess kind of a challenging problem to solve, which is why it's kind of been the theme for a lot of, for chess competitions and amateurs and professional chess players and everything. It's a challenge. So straightforward search of the space would not terminate during either player's lifetime. So you can't use, which is another interesting challenge, you can't use a standard search. They used to call it an exhaustive search, which is the term I use, which means just try everything, all the different combinations, so you're exhausting all of the different combinations. You can't do an exhaustive search on that. You won't live long enough. So games in general can simply use a search like a puzzle, which is what you're doing in the midterm, if you choose to do that problem. Solving, since you have an opponent and you're solving a puzzle, or you might need to have both a good generator and a good tester, or a heuristic knowledge that is going to help you with both as a generator and a tester. And by the word heuristic, it means some mechanism of knowing knowledge. So also on the midterm, you have heuristic searches to consider. And so those heuristic searches basically are knowledge-based or informed searches, and they're using a heuristic, which means you know a piece of information about something and you're looking for that pattern, or you're looking for that trend with the information. So it's giving you that ability. Then we have ply. So some writers use the term ply to mean that a single move by either player. So instead of doing one move by each player is considered a ply. So some insist that the ply is made up of a move and a response, and then some common use of the first definition. So ply is the same as the dep minus 1 of the decision tree rooted back to current game state. So we have an interesting concept when we have one player playing against another player, single ply games, add another extremely important piece of information to the game playing scenario, which makes it unique and why game playing is a separate category of AI. Because when you're playing and solving a problem, you don't normally have the problem working against you. So in game playing with two players, one player is trying to make the other player lose. They're not helping you. So that adds another piece of information to the game and adds a little bit of more difficulty in terms of generating solutions because the problem's it's not static, it's dynamic. It keeps changing, and it's changing not in your favor if you're playing against a good player. If you're not playing against a good player, then it's the same normal problem that you'd normally think of in other AI solutions. So there's no counter agent in there working against you at the same time. So static evaluation function. So used by the tester, generally only need to apply it to the leaf nodes of the game tree, the end pieces of the game tree to see, well, where are you? Where's the final result of each one of the paths? You're going to find it on the leaves. So this would be used by the tester, static evaluation functions. So we have Turing for test is the sum of the white values divided by the sum of the black values in terms of pieces, perhaps. Samuel's checkers, linear combinations of interactions in terms of piece advantages, capabilities and for advancements, control of the center, threat of a fork, or mobility. I haven't played checkers in so many years, actually, which is kind of interesting. I probably should play checkers. It was a fun game. I never liked chess, though, but checkers was always good. The problem with chess is it's too much of an investment of thinking. I always like those games, you just roll the dice and you move your pieces around. There's no strategy to that. It's just the luck of the roll, but you know what? There is a strategy to it. So it depends on the combinations of the rolls that you get. And if you've ever noticed, like Monopoly and stuff, some people just win because they're sitting like third in or fourth in on the rolls, and it's the position you're rolling in is what's making you win. So, which is kind of interesting. There's so many theories on Monopoly out there too. So if this was a rainy day, you guys could go home and start playing games and consider that part of your AI research. So, all right. So the role of learning, which is different. So in game playing, we have two people who are one person's making the other person lose, hopefully. And then we also have learning, so we're learning while we're playing the game. So initially, Samuels didn't know how to assign the weights for each one of the terms for his static evaluation function, because you should be learning. You're not going to make the same mistake twice, which is how people lose at chess. They don't learn it. So they continuously make the same wrong moves and the same wrong patterns, and they go down the wrong path every single time. Once the other player learns the wrong paths, well, then you play to make you expose it essentially by playing it to your advantage. So through the self-play, the weights were adjusted to match the winner's values, and then the winner's moves were heavier weight and selections and choices. So here's our tic-tac-toe, and yeah.
When you have two-player games, if you will, you have player one playing versus player
Yep.
two. What is the role of basically, you're not making the moves, you're just providing them.
The scenario is not necessarily an AI. It's an AI approach when the computer solves or the computer plays the human. When the two people play each other, it's not really considered artificial intelligence because it's human intelligence. And the artificial engine is just the game. It's just keeping track of the statistics and the scores. If the game was telling, and there's some games that do this actually, you can learn how to play chess by playing a computer, and a computer's going to tell you all your bad moves. That's artificially intelligent. In fact, there's a board they used to have on the market that lit up, so it was telling you where to put your move, what square, what position you were supposed to put something in, and then if you didn't do it, it would immediately tell you that you lost. If that was a critical move in your path and you didn't take it, that means you just lost. So it's like negative reinforcement. It means, okay, so maybe I should move it. I'll move something there. And if you move the wrong piece there, or you did the wrong move but you still occupied the same space, it would give you some other signal or something. That would be artificial intelligence as well. So you guys all played tic-tac-toe before. So everyone goes for the center for some reason immediately. You don't necessarily have to. You can still win without using the center. But ignore all the other cases in a particular case here because this one's already won, or it hasn't won, This is going to be a tie depending upon who's next. Because this person's going to go, well, actually, maybe not. So you can take down all the different possibilities to get down to the end. And actually, here's a winner here. And, you can kind of figure out what angle is going to be the most advantageous given the two players. But one player is playing against the other player. So 100A plus 10 plus 10B plus C, and you can do the calculations in here. And it's just the number, A is the number of 3 X's, 2 X's, 0 X's, and you can actually do a probability statistical thing, Percentage of times that an X gets into the square or 0 gets into the square, the chances of winning, things of that nature. So tic-tac-toe makes itself well for kind of a sample solution. Sort of an example if A was 0 and D was 0 and B was 0, and you can put it all together. You can kind of see what's going to happen here depending upon whose turn it is. So if that gets an X, then O X, that's going to be a tie. So weakness. All static evaluation functions suffer from 2 weaknesses, and a static evaluation function is one in which the game doesn't change. Going through the same route, and you can tell from looking at the leaf nodes who's going to win and who's going to lose, which means one player is not making the other player lose badly or lose when they could have won given your choices. It's static, it doesn't change. So the information information loss as a complete state. We don't have a complete state of the information. And the information mapped to a single number or to a single value on a leaf node, which might not be realistic for a kind of solution for all types of games. And here we have the credit assignment problem, giving you a credit score or credit value given your move. So it's extremely difficult to determine which move in a particular sequence of a moves causes a player to win or to lose, or how much credit to assign for each one of the end results, which is kind of like what that game does. So the game that lights up the squares and teaches you how to play chess is that it counts up and gives you points or credit scores, and then if you get to a certain point and it's 0, it knows you lost because you don't have any more points left. You've lost all your points, which means you can't win the game. When you think about it, though, isn't that kind of like the game of life? Our credit scores. It adds up and gives us a point value. Actually, the credit score is a game weakness because what does 600 or 700 mean, really? But that's a number that's based upon how much you pay your bills, how fast you pay your bills, how much you've loaned, how much you've borrowed, all the different scenarios. Then you get a number. You get a number score. So that's a static formation. So what do we need for games? A plausible move generator, a good static evaluation function, hopefully, some type of search that takes the opponent's behavior into account for non-trivial games. So we have to consider what the opponent's going to do as well. Here's a one-ply Minimax solution using a tree, and you'll have something like this actually. One of the last problems, I believe, as you work with Minimax as a concept. And this was covered in the first weekend lecture towards the end as well. So if you're not familiar with the terminology, you can either look in the book or some of the previous lectures I've gone over. If the static evaluation is applied to the leaf nodes, we get B is equal to 8, C is equal to 3, D is, let's say, -2 in this particular case. So the best move would be B, the highest number. So we can look at the maximum depth and find the minimum, A to B is the minimum move choice. So we're going to start on the left, move to the right. It just happens to be that way, actually. We could start in a different position if the numbers worked out right. Here's a 2-ply approach with 2 players. So applying the statistic evaluation here with a function, we can figure out which one's going to be the best move, depending upon the combination, so we know which route to take to get there. So propagating values, so we depend on the level, perhaps. So you could take the entire game, in fact, you could take a chess game and put it into a tree like this, actually, and have the path given different levels. So at this level, at that level, and then if you do that, then you can alternate, depending upon what your opponent has done, change your path at a particular level to change your strategy. And in that particular case, it lends itself well to evolving less static type of formation to the solution. So assuming that the minimizer chooses from the leaf nodes B would get this particular score. The maximizer gets to choose from the minimizer's values and select a C as an example, because you're playing against a component. So depending upon how the component moves, you might not have that move available to you, which is kind of the interesting part about chess, because you can plan the moves out, but you don't know what your opponent's going to do, and your opponent's working against you. So it's going to change at each one of the levels if you match it out. So a Minimax algorithm in general kind of resembles this sort of logic. If the limit of the search is reached, then compute the static value of the current position and then return the result. Else, if the level is minimizing level, then use the minimax on the child of the current position and report the minimum of the child's results. Else, use the minimax on the child of the current position and then report the maximum of the child's results. So you can kind of see how you can algorithmically go through and compute what you're looking at. We also have the search limit as a concept. Has someone won the game? We can search to see if someone has won a game at different levels. If it comes out to be true, with no likelihood of there ever being any chance for the other player to win, then the game's over without the game actually being over. The number of plies explored so far is also a factor. Also, how promising is the path? In fact, at the Wampus game, you can go down areas and end up in holes and find a less promising path. And how much time is left if it's a timer, which is kind of an interesting concept, because if you put a timer on a chess game, you change the dynamic of the game, because now your search is limited to the amount of time that you have to think about it. If you don't think that quickly, you don't have enough time to answer. You can't make a logical choice. You just do something at random just to make your turn work. Or you can do no turn at all if you wanted to. And also, how stable is the configuration? How well defined are we representing the knowledge? And this is actually a good example. Game playing is a good example of knowledge representation. Going back to what I started with yesterday, talking about knowledge representation. We're representing the knowledge of the moves of the game in a algorithmic approach, so we can analyze the moves to maximize our benefit of winning, or our chances of winning. So we're representing the knowledge that's being represented is the game moves, the positions that things can go into. So we have some criticism of this technique using the Minimax. The goodness of the current position translated to a single number without knowing how the number was focused on us. Well, that's the same problem that we have with credit scores. We don't know how that number was generated, so what value does it have? We place a value on it. Also suffers from horizon effects. A win or a lose might be in the next play, and then we would not necessarily know it, because we haven't looked in the horizon. We haven't seen past the current move, perhaps. We haven't seen past the series of moves that we've considered. So Minimax with an alpha-beta pruning kind of an approach. The alpha cutoff, so whenever the minimum node descendant receives a value less than the alpha, so we can kind of come up with an alpha number for that, known as the minimum node's parents, which will be the maximum mode. The final value of the minimum node can be set to the beta. Or the beta cutoff, whenever the maximum node descendant receives a value greater than that of the beta node, then we can do the parent node or the minimum node, and the final value of the maximum node can be set to the alpha. So we can kind of take an alpha or beta kind of pruning approach to it to minimize and to better define the values, to make it more, make it essentially more knowledgeable. So alpha beta assumptions, the alpha beta value essentially set to, and I don't know what that figure is, never decreases. Well, that's kind of a weird thing in the slide here. We set it to some initial value. It never increases, never decreases, never changes, so we can make adjustments to it. And it always current the largest backed up value found in the node successor, or the beta value, which is always the current smallest backed up value that might be in the node successors. So here's an alpha beta pruning example as an example, and I believe this is the infinity symbol here then. Infinity, and never decreases. I believe that's what those special characters are in the slide, but it doesn't really matter. The concept essentially is being being applied in this particular example where we're looking at the values that we're going to put, and we're going to either increase or decrease or traverse through depending upon what level we're on. So here's a changing or modifying the values, so we're going to get slightly different output A, B, C, D, E, F, G. We have H coming in, which is the same basic, different pattern of the leaves is going to come out of this depending upon how we're applying it. So we have different end nodes. These are the leaf nodes that we're trying to get to. So alpha betas with perfect ordering, more static evaluations are skipped, which means we don't actually have to go through and exhaust the entire area. And even without perfect ordering, many evaluations can be skipped as well. What we want to do is skip things that we don't necessarily have to worry about. If first pass are explored, the first no cutoff will occur at all. And if perfect ordering or alpha beta lets you examine twice the number of ply that the minimum max without alpha beta can examine, well, you get more for your buck in terms of the moves and the evaluations. So it's a little bit more effective. So following is a C++, no, it looks like a C-ish pseudocode explanation of the implementation of this. Not really going to go through it because we're not really looking at the implementation. It's just basically what kind of overall concepts associated with game playing should we be concerned with. So that's the pseudocode. This is actually the C++, it looks like, implementation of it. So I'm going to kind of skip through that. It might be interesting if you're implementing something in C++ to take a look at that source code. But I'm going to go ahead and fly through it here. So horizon heuristics, looking out into the future of the game to see what's going to happen next. The horizon essentially is the end result, or the entire playing scenario that might occur. And looking at and applying some heuristics to it gives us informed information about what's going on. So 3-ply search followed by a 4-ply, followed by a 5-ply, etc. until it runs out might be a progressive deepening, where we go 2 to 3 to 4, and we progress through at different stages. We also have what's called heuristic pruning that could exist. So we're ordering the moves based on the plausible and eliminating unlikely possibilities, hopefully. Doesn't come with Minimax guaranteed. It's something you would have to build in. Or heuristic continuation, extending the promising or the vital paths of 1 or 2 or more steps before committing to a choice. So we're taking multiple options. In fact, that's what we do with checkers. You put something there and you go, I might have it here, I might have it here. Depends on what's going to happen next, depending upon where your X's are, if you're the X player. Wherever they put the O is going to determine, but you might have multiple choices, and you might explore both of them until you actually decide you're going to win, until you decide you're going to place that winning one, which would be a continuous heuristic, actually, that you're practicing. Let's see, we can stop the exploration when improvements are marginal, and we can say, this is what we do with chess, and we just say, hey, we're just going to cut it off. At one point, we know we're going to win. So, hey, I've already won, or you've lost. And you can kind of play it out, all the different scenarios, and actually see that, yeah, it's true. And it doesn't come with a min-max guarantee either. Or secondary searches, once you pick a path using a 6-ply search, continue from a leaf node with a 3-ply search to confirm the pick, to say, nope, that's wrong. Nope, that's wrong. And people do that with chess, actually. They'll go through the moves, and they'll go through the different scenarios, and they'll play it out, and they'll go, yeah, that is wrong. Yeah, that's wrong. That's wrong. That's wrong. That's wrong. Oh, this one's right. So, then we have book moves. It eliminates the search in specialized situations. Does not come with Minimax guarantees. And the book moves are more like, this is how you're supposed to move it, and this is how you're, this is the predetermined way of winning the game. Nobody actually learns that. We kind of figure that with the tic-tac-toe game, you kind of just figure it out. So first person's probably going to take the center square and then move from there. So it's kind of predictable, but kids don't know that. So it's kind of interesting. In fact, that's one of the interesting things about game playing in general is all games are solvable. There is a solution to it, which is why they make really fun artificial intelligence programs. Because you can go through and figure out and program a computer to do it for you. But it's really the level skill of the player that's making it interesting. So games are designed for people to entertain other people, I guess. Who knows? By demonstrating or not demonstrating skill in the game. So Well, that was really quick, and it's only 3 o'clock. So we have choices. So let me stop the video.